When most people think about the age of the dinosaurs, they picture a world of enormous creatures stomping across dry land. Tyrannosaurus rex hunting across open plains. Brachiosaurus stretching its neck into the treetops. Triceratops facing down predators in a cloud of dust. The land was spectacular, no question, but while all of that was happening on shore, something just as dramatic, and in many ways even more extraordinary, was playing out beneath the waves. The Mesozoic era, which lasted from roughly 252 million years ago to 66 million years ago, was not just the age of the dinosaurs. It was also the age of the great marine reptiles. And the ocean during this period was as dominated by giant reptilian predators as the land was. Creatures that had evolved from land-dwelling ancestors returned to the sea and adapted so completely to ocean life that some of them never needed to come ashore at all. Creatures that were, in some cases, longer than a school bus, faster than most modern fish, and more perfectly designed for hunting in the open ocean than almost anything that has existed before or since. This is their story, and it begins not in the ocean, but on land, because every single one of these remarkable animals traces its ancestry to creatures that once walked on dry ground. The transition from land to sea is one of the most dramatic evolutionary journeys any animal can make. It requires fundamental changes to almost every system in the body: the way you breathe, the way you move, the way you regulate your temperature, the way you reproduce. And yet, reptile after reptile made that journey during the Mesozoic, drawn by the extraordinary abundance of food that the ocean offered. The story of how reptiles conquered the ocean is one of the most compelling examples of evolutionary adaptation in the entire history of life. It happened not once, but multiple times, independently, in different groups of reptiles, across tens of millions of years. The ocean kept calling, and reptiles kept answering. Each time, the result was a group of animals more perfectly suited to ocean life than the last. And each time, the ocean that received them was a richer, more dangerous, more spectacular place than it had been before. To understand why so many reptile groups made this transition, you have to understand what the Mesozoic ocean had to offer. By the time the first marine reptiles appeared, roughly 250 million years ago, the ocean had already recovered from the worst mass extinction in Earth's history. The Permian extinction, which had wiped out up to 96% of all marine species. That recovery had taken millions of years, but by the early Mesozoic, the ocean was rich again. Ammonites were everywhere. Fish were abundant and diverse. The shallow seas were teeming with prey. For any predator capable of accessing that food source, the ocean was an almost unlimited buffet. And reptiles, with their sharp teeth, strong jaws, and ability to hold their breath for extended periods, were very well positioned to take advantage. The three main groups that rose to dominate the Mesozoic ocean were the ichthyosaurs, the plesiosaurs, and the mosasaurs. Each appeared at a different time, dominated for a different period, and took a completely different approach to ocean life. Their stories are remarkable individually. Together, they paint a picture of an ocean so full of large, fast, powerful predators that it bears almost no resemblance to the one we know today. Together, they ruled the seas for nearly 200 million years, longer than the entire span of time that has passed since the dinosaurs went extinct. What makes their story even more remarkable is that none of them were inevitable. Each group arose from an ancestor that had no particular predisposition toward ocean life, that was doing perfectly well on land or in freshwater, and that stumbled into the sea through a gradual process of adaptation driven by opportunity. The ocean did not summon them. It simply rewarded them generously every time one of them took a step toward the water. The ichthyosaurs were the first of the great marine reptile groups to appear, and in some ways, the most remarkable. They arose around 250 million years ago in the aftermath of the Permian extinction, and they would go on to dominate the oceans of the Triassic and early Jurassic periods for over 100 million years. Their name means fish lizard, and when you look at their fossils, you understand why. An ichthyosaur looks, at first glance, almost exactly like a modern dolphin. The same streamlined body, the same large eyes, the same horizontal tail fluke, the same dorsal fin on the back. They are one of the most striking examples of convergent evolution in the history of life, the process by which completely unrelated animals, facing the same environmental pressures, independently evolve the same solutions. The ichthyosaurs did not start out looking like dolphins. The earliest ichthyosaurs, from the very beginning of the Triassic period, were more eel-like, long, flexible creatures that probably swam with a sinuous, side-to-side motion, like a modern eel or sea snake. But over millions of years of evolution, their bodies changed. Their limbs shortened and broadened into paddles. Their spines stiffened. Their tails developed the crescent-shaped flukes that are the hallmark of fast, efficient ocean swimming. By the time the classic ichthyosaur body plan was fully established, these animals were among the fastest and most agile swimmers in the ocean. How fast could they swim? Estimates based on their muscle mass, body shape, and tail structure suggest speeds of around 25 miles per hour, and may have been capable of short bursts even faster than that. For comparison, a bottlenose dolphin typically cruises at 12 to 15 miles per hour. The ichthyosaurs were built for speed in a way that very few ocean animals, before or since, have matched. Their eyes are another remarkable feature. Ichthyosaurs had some of the largest eyes, relative to body size, of any animal that has ever lived. The largest ichthyosaur eyes were over 10 inches in diameter, roughly the size of a dinner plate. Eyes that large serve one primary purpose: gathering light in low-light conditions. This tells us that ichthyosaurs were hunting in the deep ocean or in the dark of night, chasing prey in conditions where vision would be extremely limited for most animals. Their enormous eyes gave them a dramatic advantage in the dark. Some scientists believe they may have been the Mesozoic ocean's primary nocturnal hunters. Ichthyosaurs gave birth to live young in the water. We know this because fossilized ichthyosaurs have been found with the preserved skeletons of babies inside them, clearly in the process of being born tail first, exactly as modern dolphins give birth. This tells us they were completely independent of the land. They could not come ashore to lay eggs the way sea turtles do. They were as committed to the ocean as any animal could be, born, living, and dying in it. One of the most extraordinary ichthyosaur discoveries in recent years was the identification of a truly gigantic species, Shonisaurus sicaniensis, from fossils found in British Columbia, Canada. This animal was estimated to be over 70 feet long, making it one of the largest animals ever to have lived on Earth. For context, a blue whale, the largest animal alive today, typically reaches around 80 to 100 feet. The idea that an ichthyosaur approached the size of a blue whale is extraordinary, and it tells us that the Triassic Ocean was productive enough to support predators of almost unimaginable scale. The last ichthyosaurs disappeared around 90 million years ago, about 25 million years before the asteroid that ended the age of the dinosaurs. Their 160 million year reign makes them one of the most successful groups of large marine predators in the entire history of the ocean. If the ichthyosaurs were the ocean's answer to the dolphin, then the plesiosaurs were its answer to something that has no modern equivalent. And that is part of what makes them so endlessly fascinating. Plesiosaurs appeared around 200 million years ago and survived right up until the mass extinction 66 million years ago, making them contemporaries of the dinosaurs for almost their entire existence. They came in two very different body types, each representing a completely different approach to life in the ocean, and one of those body types gave rise to one of the most persistent legends in the history of human folklore. The first group are the long-necked plesiosaurs, the ones most people picture when they think of the word plesiosaur. These animals had small heads, extremely long necks, broad, flat bodies, and 4 large paddle-shaped flippers that they used to fly through the water in a motion more similar to a bird's wings than a fish's tail. The neck of some species was extraordinary. In Elasmosaurus, one of the most extreme examples, the neck contained 72 vertebrae and made up more than half of the animal's total body length. An adult Elasmosaurus could be up to 46 feet long, with a neck stretching nearly 23 feet. Picture a body about the size of a large car, with a neck longer than a telephone pole and 4 flippers the size of surfboards. That is an Elasmosaurus. What were those extraordinary necks for? This has been debated by scientists for over 150 years, and the honest answer is that we still don't know for certain. The most widely accepted theory is that the long neck allowed plesiosaurs to approach schools of fish from below or from the side without disturbing them with the bulk of their body. The neck could snake forward into the school, while the body remained at a distance. Others have suggested the neck was used to probe the seafloor for prey, or that it gave the animal a wider field of vision while keeping its body still. Whatever the reason, the long neck was clearly successful. It persisted in the plesiosaur lineage for over 130 million years. The second group of plesiosaurs took exactly the opposite approach. The pliosaurs, sometimes classified separately, sometimes grouped with the plesiosaurs, had enormous heads, very short necks, streamlined bodies, and 4 massive flippers. They were not stealth hunters like their long-necked relatives. They were ambush predators and open-water pursuit hunters, the apex predators of their time. The largest known pliosaur, Predator X, formerly named Pliosaurus funke and discovered in the Arctic archipelago of Svalbard, was estimated to be around 40 to 50 feet long, with a skull nearly 10 feet in length. Its bite force has been estimated at over 30,000 pounds per square inch, roughly 4 times the bite force of a saltwater crocodile, which is already one of the most powerful biters alive today. Predator X was by any measure one of the most formidable predators in the history of the ocean. It hunted other marine reptiles, large fish, and anything else it could catch in the open sea. Its four flippers gave it extraordinary maneuverability. It could change direction rapidly, accelerate from a standstill, and match the movements of fast-swimming prey in a way that a tail-driven swimmer cannot. Finding the fossils of an animal this powerful in the Arctic is a reminder that the Mesozoic ocean was warm enough, even at high latitudes, to support predators of this scale. Now, we cannot talk about plesiosaurs without addressing the most famous alleged sighting of a plesiosaur in the modern world: the Loch Ness Monster. The idea that a plesiosaur could have survived in a Scottish lake for 66 million years after the rest of its kind went extinct is not scientifically credible. Loch Ness is far too cold, too small, and too food-poor to support a large reptilian predator. It was also covered by a mile of glacial ice as recently as 10,000 years ago, making it impossible for any large animal to have been living there continuously. But the reason the Loch Ness legend resonates so powerfully, and has done for nearly a century, is that the plesiosaur body plan is genuinely one of the most dramatic and distinctive in the history of life. A long neck rising from a large body in dark water is exactly what a plesiosaur looked like. The legend is a tribute to how extraordinary these animals really were. The mosasaurs were the last of the great marine reptile groups to appear, and arguably the most spectacular. They arrived relatively late in the Mesozoic story, around 98 million years ago, but they made up for their late start by dominating the ocean with a completeness and ferocity that neither the ichthyosaurs nor the plesiosaurs had quite matched. By the end of the Cretaceous period, mosasaurs had spread to every ocean on Earth, reached lengths of over 55 feet in the largest species, and established themselves as the undisputed apex predators of the global ocean. Nothing in the sea was safe from the largest mosasaurs. Nothing. Mosasaurs were not dinosaurs. They were not closely related to the ichthyosaurs or the plesiosaurs either. Their closest living relatives are, surprisingly, the monitor lizards, the group that includes the Komodo dragon. If you want a rough mental image of what a mosasaur ancestor looked like before it entered the water, picture a very large, very fast monitor lizard. Now imagine that animal spending more and more time in shallow coastal water chasing fish. Then imagine its descendants, over millions of years, becoming progressively more adapted to aquatic life, limbs shortening and flattening into paddles, body becoming more streamlined, tail developing a vertical fluke for powerful propulsion. That is the story of mosasaur evolution compressed into a paragraph. The variety of mosasaur species was extraordinary. Some were relatively small, around 10 to 15 feet, and hunted fish and squid in shallow coastal waters. Others were specialized shell crushers with blunt, rounded teeth designed for cracking open the hard shells of ammonites and sea turtles. And then there were the giants. Mosasaurus itself, the animal that gives the group its name, first discovered in a limestone quarry in the Netherlands in the late 18th century, was around 50 feet long. But the largest known mosasaur, Tylosaurus proriger, may have exceeded 55 feet, with a skull alone nearly 6 feet in length. Some fragmentary evidence suggests even larger animals may have existed. In the warm, food-rich Cretaceous ocean, there appears to have been almost no upper limit to how large a mosasaur could grow. The discovery of the first mosasaur fossils in the 1760s and 1780s was a watershed moment in the history of science, not just paleontology, but science in general. When the enormous skull of a mosasaur was pulled from the limestone mines of Maastricht in the Netherlands in the 1770s, it was unlike anything anyone had seen before. It was clearly a reptile. The teeth and jaw structure were unmistakable. But it was enormous, and it came from rock layers that were clearly ancient. At a time when the concept of extinction was not yet fully accepted, when many scientists still believed that God would not allow any of his creations to disappear, the mosasaur skull was deeply troubling. Here was an animal that clearly no longer existed. It was one of the first pieces of concrete evidence that species could go extinct, and it helped pave the way for the revolutionary scientific thinking that would eventually lead to Darwin's theory of evolution. Mosasaurs were almost certainly warm-blooded, or at least able to regulate their body temperature more effectively than modern cold-blooded reptiles. Evidence from the chemistry of their bones and the environments they were found in suggests they were active, fast-swimming predators capable of sustained high-speed pursuit, rather than the ambush hunting style of a crocodile. They had forked tongues like their monitor lizard relatives, which they used to sense chemicals in the water, effectively smelling the ocean around them to detect prey at a distance. They gave birth to live young in the water, like the ichthyosaurs, and the largest of them, cruising through the warm Cretaceous seas, would have had essentially no natural predators in the ocean at all. They were the undisputed rulers of the late Mesozoic Sea, until the day something arrived from space that no amount of evolutionary adaptation could prepare any living thing for. To truly appreciate the marine reptiles, you need to understand the ocean they inhabited. The Mesozoic ocean was profoundly different from the one we know today, warmer, more widespread, and in many ways more extreme. And it was a world in which being large was not just an advantage, but almost a necessity, because the competition and the prey were equally extraordinary. The Mesozoic was a time of greenhouse climate. There were no polar ice caps for most of the era. The ocean covered a larger proportion of the Earth's surface than it does today, because without glaciers locking up water as ice, sea levels were much higher, in some periods by over 600 feet compared to today. Large, shallow inland seas covered areas that are now dry land. The famous Western Interior Seaway, for example, was a shallow sea that split North America in two from the Gulf of Mexico to the Arctic Ocean during the Cretaceous period. And it was home to mosasaurs, plesiosaurs, and a remarkable variety of other marine life. The water temperature in the Mesozoic Ocean was significantly warmer than today. Even the deep ocean was warmer. Estimates suggest the deep water temperature in the Cretaceous was around 50 to 60 degrees Fahrenheit, compared to roughly 35 degrees today. Surface waters in tropical regions may have reached 95 degrees Fahrenheit, warmer than a hot bath. These warm, nutrient-rich waters supported an extraordinary diversity and abundance of life. Ammonites, the coiled shell relatives of squid and octopus, were so numerous and so diverse that their fossils are found in marine rocks on every continent. Fish were spectacularly diverse, including giants like Xiphaxtinus, a 20-foot predatory fish with a mouth full of fang-like teeth that has been found fossilized with other large fish still inside its stomach. The food web of the Mesozoic Ocean was complex and layered. At the base, microscopic algae and plankton fed on nutrients in the warm, sunlit surface water. Small fish and invertebrates fed on the plankton. Larger fish fed on them. And at the top, the marine reptiles fed on everything. The competition between different groups of marine reptiles and between marine reptiles and the large predatory fish of the time must have been intense. The ocean was full of large, fast, sharp-toothed animals all competing for the same prey. And the evolutionary arms race between predator and prey during this period drove the development of some of the most specialized and efficient hunting adaptations in the history of ocean life. One of the most fascinating aspects of the Mesozoic marine ecosystem is how the three main groups of marine reptiles coexisted. Ichthyosaurs declined and disappeared before the mosasaurs rose to dominance. But during the periods when two or more groups overlapped, they appear to have occupied different niches in the ecosystem rather than competing head-to-head. Ichthyosaurs were speed hunters of fish and squid in open water. Long-necked plesiosaurs were more specialized for certain prey types and habitats. Pliosaurs were ambush predators of large prey. Mosasaurs were generalist apex predators capable of taking almost anything. Each group had its own strategy, and the ocean was large enough and rich enough to support all of them. One creature that deserves special mention in the context of the Mesozoic ocean is not a reptile at all. It is a shark. Cretoxyrhina mantelli, sometimes called the Ginsu shark, was one of the largest sharks of the Cretaceous period, reaching lengths of around 20 feet. It shared the ocean with mosasaurs and plesiosaurs, and the fossil record shows evidence of direct competition between them. Mosasaur bones have been found with Cretoxyrhina bite marks, and Cretoxyrhina teeth have been found embedded in mosasaur bones. The sharks and the marine reptiles were not just neighbors in the Mesozoic ocean, they were rivals. Everything we know about the marine reptiles comes from fossils, and the fossil record of these animals is, by the standards of paleontology, remarkably good. Marine environments are ideal for fossil preservation because sediment accumulates steadily on the seafloor, burying the remains of animals that sink to the bottom after death. The result is that marine reptile fossils are found on every continent on Earth, in marine rock formations ranging from the Triassic to the end of the Cretaceous. And they include some of the most complete and beautifully preserved vertebrate fossils ever discovered. Some of the most important marine reptile fossils have come from unexpected places. The Solnhofen limestone of Bavaria in Germany, the same rock formation that produced the famous Archaeopteryx fossils, has yielded exquisitely preserved ichthyosaurs with the outlines of their soft tissue visible in the rock, showing us exactly what their fins and body shape looked like in life. The chalk formations of Kansas, once the floor of the Western Interior Seaway, have produced spectacular mosasaur and plesiosaur skeletons, some of them complete enough to reconstruct every detail of the animal's anatomy. The Svalbard archipelago in the Norwegian Arctic has produced some of the most dramatic pliosaur fossils ever found, including the skull of Predator X that we mentioned earlier. And the coastal cliffs of Lyme Regis in England, where waves constantly erode the ancient Jurassic rock, have been producing ichthyosaur and plesiosaur fossils for over 2 centuries. In recent years, advances in imaging technology have revolutionized what we can learn from marine reptile fossils. CT scanning allows scientists to look inside bones without damaging them, revealing internal structures that tell us about growth rates, metabolism, and evolutionary relationships. chemical analysis of fossilized bones and teeth can reveal information about diet, body temperature, and even migration patterns. The oxygen isotope ratios in fossil teeth can tell us the temperature of the water the animal was swimming in. Melanin preserved in fossilized skin has revealed that at least some ichthyosaurs had dark-colored skin, possibly like modern dolphins, as a form of camouflage or thermoregulation. One of the most remarkable recent discoveries was the identification of ichthyosaur skin pigmentation. In 2018, scientists analyzing an exceptionally well-preserved ichthyosaur fossil from the Jurassic of Germany found traces of melanin preserved in the fossilized skin, the same pigment that gives color to the skin of modern animals. The evidence suggested the ichthyosaur had dark-colored skin, possibly counter-shaded like a modern shark or dolphin, darker on top, lighter on the bottom, which is a form of camouflage that makes an animal harder to see from both above and below. It was the first time direct evidence of skin coloration had been found in a Mesozoic marine reptile, and it brought these ancient animals one step closer to life. New species of marine reptiles are still being discovered regularly. In 2023, scientists described a new giant ichthyosaur species from fossils found on the Somerset coast of England, one of the largest ichthyosaurs yet identified. New mosasaur species have been found in Morocco, Angola, and New Zealand, each adding to our picture of how these animals spread across the global ocean. New plesiosaur material from Antarctica has confirmed that these animals lived in polar waters too, hunting in the cold, dark seas at the edges of the Mesozoic world. The age of marine reptile discovery is far from over. Perhaps the most important lesson from the fossil record of marine reptiles is how much remains unknown. We have a good picture of the major groups and the largest species, but the ocean is vast and the fossil record is incomplete. For every spectacular skeleton that was buried in just the right conditions, preserved through millions of years of geological change, and then exposed by erosion at exactly the right moment to be found by a scientist or a sharp-eyed amateur fossil hunter, countless others were lost. The animals we know about are almost certainly a small fraction of the true diversity of the Mesozoic ocean. Every new discovery reminds us how much the rocks still have to tell us. The story of the marine reptiles ends, like so many stories from the Mesozoic, with an asteroid. 66 million years ago, a rock roughly 6 miles across, traveling at around 40,000 miles per hour, struck what is now the Yucatan Peninsula of Mexico. The impact released energy equivalent to billions of nuclear bombs. The immediate effects were catastrophic. A fireball that ignited forests across a wide region, a mega tsunami that swept coastal areas, earthquakes of unimaginable scale, and a pressure wave that circled the globe multiple times. But the longer-term effects were even more devastating than the immediate impact. The asteroid impact threw an enormous quantity of dust, soot, and debris into the upper atmosphere, where it spread around the entire planet within days and blocked sunlight for months, possibly years. Without sunlight, photosynthesis stopped, plants died, the food chain collapsed from the bottom up. On land, the non-avian dinosaurs disappeared, along with roughly 75% of all species on Earth. In the ocean, the effects were equally devastating. The plankton that formed the base of the marine food web were wiped out almost instantaneously. The ammonites, which had been one of the most successful and diverse groups in the ocean for hundreds of millions of years, went completely extinct. And the mosasaurs and plesiosaurs, the apex predators that had ruled the seas for tens of millions of years, vanished along with them. The speed of the marine reptile extinction is striking. At the end of the Cretaceous, the ocean was full of mosasaurs, diverse, widespread, and at the peak of their evolutionary success. In the rocks from just after the asteroid impact, they are simply gone. No gradual decline, no transitional period, just an absence, as sudden and complete as switching off a light. The geological boundary between the Cretaceous and the Paleogene periods, the KPG boundary, as scientists call it, is one of the most dramatic dividing lines in the entire history of life. And nowhere is the contrast more stark than in the marine fossil record. Below the boundary, mosasaurs. Above it, nothing. What is particularly striking about the end of the mosasaurs is how successful they were right up until the moment of extinction. There is no evidence of a population in decline, no sign of increasing stress or reducing diversity in the millions of years before the impact. The mosasaurs were thriving. They had colonized every ocean on Earth. They had diversified into dozens of species, filling every ecological niche from shallow coastal waters to the open, deep ocean. They had no warning, no time to adapt, no chance to evolve a response to what was coming. An ocean that had been dominated by giant reptilian predators for nearly 200 million years was empty of them within a geological instant. The sharks, remarkably, survived. They had survived every previous mass extinction, and they survived this one too. In the aftermath of the KPG extinction, with the marine reptiles gone and most of their competitors eliminated, the sharks that made it through found themselves in an ocean with drastically reduced competition. Over the tens of millions of years that followed, they diversified and filled some of the niches left vacant by the mosasaurs and plesiosaurs. The ocean did not stay empty for long. Life, as it always does, found a way to fill the space left behind. But the age of the great marine reptiles was over. It would not come again. In the cold, dark, nutrient-poor ocean of the immediate post-impact years, the survivors were not the largest and most powerful. They were the most flexible. Animals that could eat a wide variety of food, tolerate cold temperatures, survive for extended periods without eating, and reproduce quickly when conditions improved. Sea turtles, small sharks, bony fish, early ancestors of the marine mammals that would eventually rise to prominence. The criteria for survival had changed completely, and the new ocean that slowly rebuilt itself over the millions of years following the impact would be a very different place from the one the mosasaurs had ruled. The marine reptiles have been gone for 66 million years, but their legacy is surprisingly present in the world we live in today. Some of it is scientific, some of it is cultural, and some of it is written in the bodies of the animals still swimming in the ocean right now. The most direct biological legacy of the marine reptiles is the sea turtle. Sea turtles are the only group of large marine reptiles that survived the KPG extinction. They managed to pull through in a way that the mosasaurs, plesiosaurs, and ichthyosaurs could not, probably because they had a more flexible diet, could survive on very little food during the dark post-impact years, and because their eggs, buried in beach sand, gave their young a degree of protection from the chaos unfolding in the ocean. Sea turtles have been swimming in Earth's oceans for over 100 million years. The leatherback sea turtle alive today is the largest living reptile on Earth and the deepest diving reptile ever recorded, capable of diving to over 4,000 feet. It is a direct, living connection to the age of marine reptiles, still navigating the same ocean, still returning to the same beaches, still using a body plan that was ancient when the mosasaurs were young. The scientific legacy of the marine reptiles is equally significant. The discovery of mosasaur and plesiosaur fossils in the late 18th and early 19th centuries played a crucial role in the development of paleontology and in the broader scientific revolution that overturned the idea of a static, unchanging natural world. Mary Anning, a self-taught fossil hunter from the English coastal town of Lyme Regis, discovered the first complete ichthyosaur skeleton in 1811 at the age of around 12, and went on to discover multiple plesiosaur and pterosaur specimens that transformed our understanding of prehistoric life. She sold fossils to support her family, corresponded with the leading scientists of her day, and made discoveries that changed the course of natural history. Yet her contributions were largely uncredited during her lifetime because she was a working-class woman without formal scientific training. Today, she is recognized as one of the founding figures of paleontology, and the famous tongue twister, "She sells seashells by the seashore," is widely believed to have been written about her. The marine reptiles also transformed how scientists and the public understood the concept of extinction. When the enormous mosasaur skull was unearthed in the Netherlands in the 1770s, it presented an uncomfortable challenge to the prevailing view that God's creation was complete and unchanging. Here was an animal, clearly reptilian, clearly enormous, that no longer existed anywhere on Earth. Coming to terms with that fact, that species could appear, dominate their world for millions of years, and then vanish completely, was one of the intellectual milestones of modern science. The marine reptiles helped make that idea unavoidable. Culturally, the marine reptiles have left a deep mark on the human imagination. The long-necked plesiosaur silhouette is one of the most recognizable shapes in popular culture, appearing in everything from the Loch Ness monster legend to countless films, books, and television programs. The mosasaur made a dramatic appearance in the Jurassic World film franchise, introducing a new generation to these extraordinary animals. And the ichthyosaur, with its dolphin-like body and enormous eyes, has become a symbol of convergent evolution, showing young scientists and curious viewers alike that evolution finds the same solutions over and over again, regardless of where it starts. There is something deeply satisfying about the fact that these animals, which ruled the ocean for 200 million years and then vanished in an instant, continue to shape how we think about life, extinction, and the history of the planet. Their bones are still teaching us things. New species are still being found, and every time a child picks up a fossil from a beach and wonders what it was, the marine reptiles are, in some small way, still alive. The marine reptiles tell us something important about the ocean that is easy to overlook. They tell us that the ocean's apex predators are not fixed. They are not permanent. The creatures at the top of the marine food chain have changed multiple times over the history of the ocean, replaced by new groups that evolved better adaptations for the conditions of their time. The ichthyosaurs gave way to the plesiosaurs and mosasaurs. The mosasaurs gave way to the sharks and the early whales. The ocean is always in the process of selecting for new champions, and no group, no matter how successful or how dominant, is guaranteed a permanent place at the top. This is a pattern that runs through the entire history of the ocean. In the Cambrian, the apex predators were animals like Anomalocaris, creatures with no living relatives that ruled a world of soft-bodied organisms. In the Devonian, giant armored fish called placoderms dominated. In the Triassic and Jurassic, the ichthyosaurs. In the Cretaceous, the mosasaurs. After the extinction, sharks and eventually whales. Each group was the product of its time, shaped by the specific conditions, prey availability, and competitive landscape of its era. Change the conditions, and a new group rises. The ocean does not play favourites. The marine reptiles also tell us how powerful evolutionary pressure can be when an environment offers sufficient reward. The ocean was rich enough, and the advantage of accessing it large enough, that multiple unrelated groups of land reptiles independently made the transition to ocean life, each time developing remarkably similar solutions to the same challenges. Streamlined bodies, paddle-shaped limbs, live birth, large eyes for hunting in low light. The ocean shaped all of them in similar ways, because the ocean's demands are consistent regardless of what you start with. This phenomenon, convergent evolution, is one of the most compelling demonstrations that evolution is not random. It is directed by the environment, and similar environments produce similar results. The story of the marine reptiles is also a story about opportunity. The Permian extinction wiped the ocean clean, and into that emptiness the reptiles came. The end Cretaceous extinction wiped the ocean clean again, and into that emptiness the mammals came. The ocean rewards groups that are in the right place, with the right adaptations, at the right moment. Timing matters as much as ability. The mosasaurs were extraordinary animals, but they needed an asteroid-free world to keep being extraordinary. And finally, the marine reptiles are a reminder of just how much of the ocean's history we are still discovering. For most of human history, we had no idea these animals existed. The first mosasaur skull was found less than 250 years ago. The first complete ichthyosaur was found just over 200 years ago by a 12-year-old girl on a beach in England. Everything we know about 200 million years of marine reptile history has been pieced together in the blink of an eye from fragments of bone buried in rock. And what we have found is extraordinary. What remains to be found may be even more so. Every year brings new discoveries, new species, new behaviours, new insights into how these animals lived and hunted and died. The story of the Mesozoic ocean is still being written, one fossil at a time. It is a story worth paying attention to. The ocean as we know it today, with its whales and its sharks and its sea turtles and its fish, is not the final version of the ocean. It is one chapter in a story that has been running for 4 billion years and shows no sign of ending. The marine reptiles were a chapter too, a glorious, dramatic 200 million year chapter filled with some of the most spectacular animals that have ever lived. They are gone now, but the ocean that shaped them is still here, still changing, still selecting for whatever comes next. We are lucky to know they existed, and the more we learn about them, the more extraordinary they become. For nearly 200 million years, the ocean belonged to the reptiles. They came from the land, adapted to the sea, and became some of the most extraordinary predators the ocean has ever known. And then, in a geological instant, they were gone, replaced eventually by the mammals and the fish and the sharks that dominate the ocean today. But their fossils remain. In the chalk of Kansas, the limestone of Bavaria, the cliffs of Lyme Regis, and the frozen islands of the Arctic. And in the body of every sea turtle gliding through warm tropical water, the age of marine reptiles is still, in a small but real way, alive. In our next episode, we go back further in time to meet the ocean's oldest and most enduring predator, the shark. A creature that was already ancient when the first ichthyosaur slipped into the sea, that survived every mass extinction, including the one that ended the age of marine reptiles, and that is still here today, essentially unchanged, still hunting the same ocean it has hunted for 450 million years. Until then, thank you for listening.